Welcome back, physics students. Today, another magic lab. Hopefully we have as much fun as we did in the last magic lab. At this point, you should have printed out the 3 sheets in the Google Stream, all 3 sheets. There are no instructions to this lab. I'm just going to walk you through the procedure. This time, what I'm going to be using is this spring-loaded cannon, and it's going to shoot out a little plastic cannonball. And the goal is first in part 1 to figure out the speed of the ball out of this cannon. Now speed, we can use distance over time, but it's not going to be as accurate as using the magical physics formulas of projectile motion. So what I'm going to do is first launch this cannon at 0 degrees. There's a little compass on this side and a string hanging down, and I've got it set to 0 degrees. And if you look, you could see that I've got a sheet of paper, a target with a bunch of carbon paper on it all across on the floor over there. I'm going to launch this 3 times, and we're going to see how consistent the dots are. And then if they're good enough, we're going to use that data, measure the horizontal distance, the vertical distance, and figure out, like we did in Magic Lab 1, the speed of these little cannonballs out of this cannon. So let me begin. I go 2 clicks in. And all I have to do to launch this is pull up on this string to release the cannon. So let's do the first trial. All right, so, I hope I can find that. So let's see. Ah, there it is. Lesson learned. All right, so now what I'm going to do is, even though I have this set to 0 degrees, I'm going to loosen it and reset it to 0 degrees. This is something that is important in measurement. If I set this to maybe ½ a degree instead of 0 degree, if I do all the trials with that same setting, every trial is going to be wrong. So what I'm going to do is re-measure to sort of randomize the error, and then hopefully maybe sometimes it's at ½ a degree to this way, ½ a degree that way, and overall the average will be straight across. So that's what I'm doing. I'm randomizing my trials by resetting it every time. All right, tighten it up nice and tight. Okay. Once again, I launch by pulling up this string. So here's launch 2. Okay. All right. Again, I will loosen this and randomize the next trial also. You know what, too? I should be loading the spring cannon, because when I push it back, I could be messing up the setting. It's a real tight spring. All right, launch number 3. Okay, so let me go have a look at our marks. Not too bad. Okay, so it looks something like this. All right, so they look more or less like this on the floor. Pretty spread out. You see, there's my hand. But I could kind of do an average by maybe going somewhere in here and measuring that. And that would be a pretty good average by going in the center of the 3 dots. That's the good average of my 3 trials. Once again, to measure that range, I need to know where to start my tape measure, where the bottom of this cliff is. Once again, I just use what we call a plumb line, or plumb bob if you'd like. By the way, if you want, you could buy these at Home Depot. They sell these for carpentry. All right, that should be good. Let's stop this from swinging. Now, I don't have a partner, so this is going to be a little tricky. Hopefully, I don't introduce enough air to take the magic away, undo the magic. So, okay. All right, so I'm going to say, based on I measured all three, and so just an average is about 331 or 3.31 meters. So I wrote that in for the range. You're going to get your own horizontal range, 3.31 meters, your own from the Google Stream. I also need the height of the launcher. So let me get that now. So there is my Y height, okay? Now, from one of these two numbers and physics projectile calculations, you need to be able to calculate the time. You got to think, is the height going to help you figure out the time, or the range horizontally going to help you figure out the time? Use one of those numbers in physics equations, and in the end, get time here. So go ahead and do that now. Okay, next thing. Once you have this time, and then whatever number you used before, you use the other one. So use the other number, and in the end, calculate V. And by the way, this is in the X direction because the cannon is horizontal. So go ahead and do that calculation now. Okay, so now if you were in class, what I would do is I would assign every group a different angle. So what I'm going to put for me is maybe I will put 50 degrees. You know what? I don't know if that's going to hit the ceiling. No, I think it's good. 50 degrees for me. But you're going to go into the Google Classroom stream and get your own angle, okay? Because what I'm going to do in the next part is I'm going to reconfigure this cannon and take it off this table. And then I'm going to, for me, right, I got 50 degrees. So what will happen is I will change this to 50 degrees, lock it in place, put a target somewhere. That's where the magic comes in. I'm going to make a prediction, right? All I did was measure things with a tape measure and the bigger magic, the physics equations. I figured out this horizontal speed, which then will be the speed up at this angle, because the spring is the same. So if this came out to be like 6 meters per second, when I go like this, it's still 6. And from that speed and the angle, I'm going to figure out where this ball lands. And then we'll put the target there, and it's going to hopefully hit the target on the first try like magic. I'll be predicting the future again. So let me reconfigure things, and then I'll explain how to do those calculations. So give me a second to reconfigure the launcher. All right, so I have the cannon set up on that far table over there, clamped to the table, and then I have this table over here where we're going to see the magic happen, hopefully, where the ball will hit the target on the first try. But first, before that happens, we have to perform the magic ourselves with, of course, the physics equations. So what you already have is the horizontal or the velocity of the cannon as a result of the spring action on the ball. Now, that was horizontal in this part. Now what we're going to do is launch it up at an angle from the angle you were assigned. Mine was 50 degrees. Here's my speed. Again, yours will be different based on your data. And of course, this launches horizontally and vertically at the same time. And the reason why we need to split this up into horizontal and vertical, because the projectile problem is exactly that. Two problems happening simultaneously, one in the x, one in the y. So based on this diagram, I can now calculate the x component here of the launch velocity. And remember, like all calculations, you have to have 3 steps here. You have to have an equation, substitution with numbers and units, and an answer with units. So go ahead and calculate the horizontal speed of your ball now. Next, calculate the vertical speed of the ball launched at your particular angles. So go ahead and do that here. Remember, equation, substitution, answer with units. So go ahead and do that now. Okay, so moving on to the next page, step 5 says, calculate the total time of the projectile's flight. A lot of people will be tempted to use the time from here, but that's a completely different time. That was when the cannon was on the desk, the teaching desk, and at a different angle. Now it's a new time. It has something to do with these velocities here. One of them you use in the calculation here, and an appropriate physics equation, and you calculate the time that it takes that ball to land. So go ahead and do that now. Calculate the time for the ball to land. Okay, on to step 6, calculate the horizontal range of the projectile. In other words, how far is this thing going to go? So again, you're using one of these here, and the data you've calculated, and you're going to figure out how far this thing goes horizontally. So go ahead and do that now. Okay, so that, by the way, you just predicted the future. Not with a crystal ball, but with physics. Even more powerful than a crystal ball. Okay, so let's see if that prediction was accurate. So now what I have to do is measure that out. So let me go to the other side. And oh, by the way, mine, as you may have seen, mine is 4.623. Yours is going to be something different because you have different data. But I need to measure out 4.623 meters. Maybe I'll leave that right here. Now, I've got my tape measure, and I've got a stack of books here with my target. Okay, and the reason why I'm putting these on a stack of books is because I want the ball to land from the same altitude it was launched at. There are ways to calculate when the ball lands at a different altitude, like if it were to land on the table. It's not in our curriculum, it's too difficult. So the books just allow the ball to land at the same altitude it was launched, but over there, of course. So I need to measure out 4.62 meters. Let me get the tape measure stretched out. Again, I don't have an assistant here, so bear with me while I struggle. Well, I'll do this, struggle through this. Okay, so there, lock that in place. Line this up. Okay. Take my target, 4.623 meters. I'm going to center it, obviously. I want this to, the ball to hit right in the center, so I'm going to do my best to center 4.623 right here. So, all right, something like that I'm thinking, okay. Okay, now I also want to have it the right distance this way. Now, for a little extra fun, I'm going to put another target here and see if I could hit the man. This to me looks like maybe an old Ken doll from Barbie set, so maybe I'll call him Ken. Ken's going to stand right here, and let's see if we could hit him. Not with a cannonball. We're going to hit him with a water balloon for fun, right? This is going to be, we don't want him to get hurt. So there he is standing. Why did I put him not at the center? Because the ball's going to be coming in like this, so it's going to land here. So if I backtrack, I'll hit him like somewhere in the upper body. That'll be perfect, or I hope it'll be perfect. I'm going to stop the camera so I could up the resolution, okay? So and then so maybe I'll be able to zoom in if everything goes well. So give me a moment. All right, here we go. I'm going to load it in. 1, 2 clicks. And now I'm going to make sure this angle is at the right, hopefully as close to 50 as I can get it. All right, I think it's good. Well, what do you think? Are we going to see the magic? Is it going to work? Here we go. I hit the target, but I did not hit. Ken survived, so let's try a little tweaking to the side. So, you know, side to side is fine, you know, but the distance in that direction is what I calculated, and I did perform magic. I hit it on the first try. So let's give it a little nudge like this. There it is. Okay, so success. All right, so as I said, I'm going to shut the camera off so I could turn the resolution back down. The next thing that I want to do is figure out the maximum angle I could go before I hit the ceiling. And to do that, I need to know how tall the ceiling is. So I'm going to measure from the ceiling down to the cannon. Okay, and I get about 1.736. 1.736 meters. And so and by the way, I jumped ahead a little bit. Before I measure this 9, you need to figure out how high your projectile goes, the maximum height. Obviously not going to hit the ceiling, but you figure that out, and you could call it dy or h, again from the data for your launch angle. The next thing, 1.73 meters, obviously will the ball hit? It's going to be no, because this will be less than this, and it will not hit. Plus we saw it didn't hit, so will the ball hit? No, that's what you write there. So next thing we're going to do is on the next page, we're going to calculate the maximum y velocity the ball can have without hitting the ceiling. Forget about all the other data except for the data I just measured, which you will get your own from the Google Stream. Take that distance alone and calculate the maximum y velocity for it to just barely touch the ceiling. So we say without hitting the ceiling, but pretend it just barely gets there and touches it like a millimeter away. So then what is that y velocity? Go ahead and calculate that now. Now, number 12, going this way this time, draw a vector diagram for the y component of the velocity of the ball and the launch velocity. So, you know, when we do a vector diagram, we draw something like this. And I'll make something up. Let's suppose this is 5.9 meters per second. You know, you'll calculate it. So where does that go? Does that go here, here, or here? Put that 5.9 in the right place in the diagram. Now, one of the other two sides is known, okay? somewhere back in the lab, you calculated either this hypotenuse or this x component for this new angle where it's about to hit the ceiling. Go back in your lab and figure out whether you're going to calculate this, or I should say which one you already calculated. Fill it in on that vector diagram. Then you're going to put theta here. All right, so now that that's complete, based on the two sides you put in here in this theta, figure out the maximum angle. It's going to be some kind of trig function here, and in the end you're going to have theta equals, I don't know, 49 degrees or whatever. So you calculate some angle. So go ahead and do that now. Step 14 has nothing to do with any of these. It says if the ball was launched at the original launch angle, in other words, this angle, what would its velocity components be at the moment of impact? Be as accurate with the signs as possible, positive or negative. So this is going to crash into the ground like this. What is this and what is that? Vx equals, Vy equals. Just write the answers, nothing to calculate in that step. So go ahead and do that now. Okay, so that was Magic Lab 2. As fun as Magic Lab 1, as amazing as Magic Lab 1, we predicted the future, where the ball would land. We had a little trouble hitting the man, so maybe fate wasn't quite cooperating. But the distance this way, we were correct on. We hit first try. Exciting stuff. What you're going to do is turn in these 3 pages, photos, as always, in the Google Stream. And I hope you enjoyed the lab. I hope you enjoyed the magic and the physics. Same thing, magic, physics. And I'll see you in the next physics video.